Welcome to course in Discrete Structures. So we'll start with a simple question: what is computer science? We'll begin by dispelling a common myth about computer science. What exactly is computer science? Is it programming in Java or C++? Is it networking via the internet, or perhaps video games and troubleshooting personal computers? The answer is that all of these are indeed aspects of computer science. They form part of the engineering or applied sides of the field, which works to create useful, reliable, and working systems. The software engineering is just part of the answer. At the heart of computer science lies a fundamental core of highly theoretical areas such as artificial intelligence, algorithms, cryptography, and even quantum computing. These areas investigate questions like how can we make a robot smart? Or how do we find the shortest path between two cities on the map? Or send a secretly coded message from one to another. So it is this theoretical foundation which makes computer science fundamentally possible. So what is discrete structures? People use interchangeably the words discrete structures and discrete mathematics to refer to topics covered in a course like this. Discrete mathematics is a branch of mathematics that forms the foundation for computer science. So discrete mathematics deals with objects that come in discrete bundles. For example, set of natural numbers. So that set of natural numbers is an infinite set, but it is countable set of numbers. Countable means that if you tell me 10, that I can count 11. If you give me any number, I can count the next one. Set of real numbers, on the other hand, is a continuous set, which is uncountable, and it's an infinite set. So both are infinite sets, the countable sets and uncountable sets, but some are countable, some are not countable. So for example, if you're given two real numbers, there can be infinitely many real numbers between them. So it's uncountable, it's totally uncountable. So in this course, our goal is to equip you with the basic tools and language you need to move forward in your study of computer science. So what's the language we are talking about? We are talking about the language of mathematics. It turns out that the underlying principles of computer science can be described very elegantly using mathematics, particularly in theoretical branches of CS. So why learn mathematics at all? You have learned branches of mathematics like algebra, geometry, pre-calculus, and what else? You have learned many things like that. But this type of mathematics, what we're going to learn here, is somewhat different. As a computer scientist, you should learn a new kind of mathematics, the mathematics of the language of mathematics. So why we learn mathematics is the ultimate truth. Once you prove something, it's hard to disprove it. Without mathematics, world cannot function. Everything in our world is mathematically based. In the heart of many modern systems is mathematics. So world runs essentially using mathematics. So the science to me, the computer science means you must be able to assure that a process can be repeated under the same conditions and get the same results. So in other words, you don't have a science if you cannot find a process that can be repeated and expect the same thing. For example, if you run a program for the same set of inputs, you must get the same set of outputs. Now it's time to learn the language of mathematics. So why study discrete math? We want to learn how to use mathematical models and methods to analyze problems that arise in computer science applications. For example, designing high-speed networks or message routing paths, or finding good algorithms for sorting and performing web searches. In other words, we have to tell the computer how to do something in a step-by-step manner. Performing web searches. Web searches have become a key part of our lives today. We cannot live without web searches. The computer security, we do a lot of things online today, and therefore the computers have to be secured, and they have to be proven to be secure. Cryptography, using a public and private keys, we can create a system that cannot be broken unless you can have a lot of processing. We'll talk about the issues associated with cryptography later in the course. So learning mathematics is an essential component of becoming a computer scientist. The science in computer science, to me, indicates that we must be able to prove and repeat our results to show their validity. Right? A programmer, on the other hand, will build some software without analyzing its impact. When we study CS, we need to ask questions like, is my program correct? Does it produce the correct output for all inputs? Does the program terminate? Does it take too much time? Is it efficient? Being able to answer these questions is critical to becoming a computer scientist. Therefore, the foundational course is critically important to your growth as a computer scientist. There are many applications of CS that requires mathematical analysis. So the key focus in this course is proofs. So what is a proof? If you write a program, that's a proof. Why do we call a program a proof? Because a proofs, that means it must be correct. It must follow logically from one sequence to the other. So if you think about a program, it's a set of instructions that logically follows from one instruction to another. If this logic fails for some reason, we call it a bug. So we have to go and look at the place where the logic failed, and we have to fix the bug. We can prove the correctness of the programs by understanding how to mathematically prove something. So proof, what is a proof? Again, a proof can be defined in many ways. One can say a proof by evidence. So we can show some evidence and say that is a good enough proof to know that this person is guilty or innocent. Proof by experiments. Scientists do this all the time. So we prove something by experiments. We conduct experiments after experiments, then they all are true. It doesn't mean that it's absolutely true in every case. So there could be some cases where the experiment could fail. But for the most part, if the experiment is under the assumptions of the experiment is always successful, then you will say, oh, that's a proof. Proof by contradiction. Sometimes you want to prove something, but proving the negation would be much easier. So for example, you want to claim that if it rains, the roads will be wet. So we know that if the roads are not wet, which is by observation, then we know it didn't rain. So therefore, we prove that if it rains, the roads must be wet. But we proved it by contradiction. We can also do proof by directly using axioms. So we have some assumptions, and then we prove the things using assumptions. So we will do a lot of those things in this course. So in general, a proof is something that we all, or most people, can agree on with sufficient evidence. So a program as a proof. So let's take a look at a piece of code. What does this code do? So we will have a proposition. We'll say, given n, this code produces the sum of the first n integers. So we can ask the question, is this always true? How do we know that this code produces the correct sum? We all know how to check by experimentation, right? We can run this for n equals 1, n equals 2, n equals 3, and then we can figure that out on paper, what we're supposed to get. For example, if it's n equals 3, we should get 1 plus 2 plus 3, that's 6. So if you run this code with n equals 3, you should get 6. But can we claim victory at this point? No, because we do not know what will happen for the integers we didn't check. Surely, we cannot check for all the n's because there are infinitely many of them. So therefore, at later stages, we have to be able to prove that this piece of code actually always produces the sum of the first n integers. So there can be a lot of other things that we can prove same way. In fact, by the way, this program cannot run unless there's an initial condition. So this initial condition is also very important for the proof that we will do later in the course. Okay, here's another statement that can be, so this is a proposition. We say there are more people living in the world today than all those people who died from the beginning of time. How can we check the truthness of the statement? One needs to construct a convincing argument, right? One possibility is to draw a curve that constantly increases. So for example, you can say, you start with 2 people, they had 2 children, so now we have 4 people. And then let's suppose that it doubled again, and it doubled again. At some point, the original people will start to die. So the question is, if you add up all of those things, can you prove that there are more people living in the world today than all those people who died from the beginning of time? So think about that. Here's another one. This is a proof of Pythagorean theorem we all learned in school. So we want to prove that c squared equals a squared plus b squared. But how do we prove that? So there are lots of ways to prove it, but one way is to give a geometric proof. So we have this square inserted into a square of all sides c inserted into a square of all sides b, a plus b. And then by using somehow an argument of area, we can do that. So for example, if you take the area of this triangle, that would be 1/2 a times b. And then you have 4 of those. and then you will try to figure that out. So I'll leave that as an exercise for you to do. So let's talk about proof. A proof is a verification of a proposition. In the context of this course, a proof is a validation of proposition. A proposition is a statement that is either true or false. How to prove something? We'll use solid axioms to prove something. Once proved, there's no doubt that the statement is true or false. Proofs are really important for critical system that we depend on every day. So imagine like the software that runs the airplane, it must be proved to be correct. If there's a bug, then the plane can crash. Or electrical grid, where we depend on electricity, that's a very critical system. So a mathematical proof is, in fact, is a verification of a proposition by a chain of logical deductions from a set of axioms. Like, in other words, logical deductions is like a sequence of valid statements, and axioms is a set of assumptions. We'll get more into this as we go. A proposition is a statement that's true or false. We can give many examples of proposition. The world population is over 6 billion. That statement is either true or false. A child can walk as soon as he or she is born. That's either true or false. But we can also give many examples of statements that are not proposition. It is 3 o'clock. Sure, this is true at a particular instance, but we do not consider this to be a proposition. How are you? This is a question, not a proposition. Wake up now, not a proposition. So let's give a definition of a predicate. A predicate is a proposition that depends on some condition for its truth value. For example, you can say for any integer n, we can write the integer n as a product of prime numbers. Is that always true? Any even integer, we can claim, can be written as a sum of two primes. Is that always true? So we can give a lot of these predicates that depends on n, for example. So in this course, we will study how, for example, we will study the mathematics that are necessary to understand things like how to diagnose systems that are inconsistent. So two propositions can be contradictory in their system, and therefore system could fail at some point. How to build a formal machine, what we call a DFA, or deterministic finite automata. How to do a formal proof using axioms, lemmas, and theorems. How to understand the models of computing, such as Turing machines. Or how to answer difficult problems, such as NP and P. Again, I'm not going to define these things, and we will get to that when we have the right time. So this course is a part of a sequence of courses. So for example, after you take this course, you can go into discrete structures, or principles of programming languages, or database systems, design and analysis of algorithm, formal languages, and so on. Now, interestingly, one of the things we'll study later are what's called the graphs. And this is an example of a dependency graph that's also a directed graph. That means you can ask a question like, if I want to take CS437, what is the best way to do that? I want to have the shortest path, because there could be many ways that I can get to 437, and so on. So let's get to the course objectives. So what we are trying to do is to understand computers as a mathematical model and write precise mathematical statements that captures what we want in each application. So we will learn to prove things about these statements. So for example, we may write a proposition that describes the system specification. So the course learning objectives more broadly is to describe a problem that is presented in a natural language like English and describe it in a precise language like mathematics. Once we introduce notations, then operations and structures, we can proving things become probably easier. So what we will do for the most part in the course is learning to become a computer scientist is a lot more than learning to program. It's not difficult to learn how to code, but it's difficult to learn how to analyze and reason about your code. So this course is all about the mathematics as a language. So computer science is no more about computers than astronomy is about telescopes. So computers are just the device, and we must learn how to program it correctly. In order to do that, we have to learn the language of mathematics. So we need to express computers and computing and algorithms using a mathematical language. So when we studied the science of computing, so we say that computation is the manipulation of information and data. Algorithm is description of how the data is manipulated. So proofs are a fundamental part of the course, quite different from checking if a program works. For a few examples, we'll try to prove that the program should work all the time. So in order to do that, you have to learn the language of mathematics. So the role of theory in CS is to build a mathematical model for computation, explore the logical consequences, and gain insights about computer science. So the theory plays a critical role in every science, and the role of theory CS is equally important. This is how we can describe things that work and not work. We can describe the possible and the impossible. We can describe a mathematical model for computation and algorithms. In the real world, we do computation, but that's expensive. Instead, in the abstract world, we can analyze the same computation using a mathematical model and ask the question, is it possible to solve this problem using a computer? How long will it take? If it's possible, how long will it take to run the program on a computer? Because computers come in many shapes and forms, we can only answer these questions using a more abstract model of computation. Formalizing propositions. So suppose we want to think about formalizing propositions that are presented to us in English sentences. For instance, this one says, you cannot ride the roller coaster unless you are over 18 years, over 5 feet tall. This can be quite confusing. There's a word called unless, there's conditions over 18 and conditions over 5. So by stealth, the statement can be confusing. If we identify the smaller components, for example, ride this roller coaster, that can be proposition. Then we can check to see if this is a consistent statement. So let's try to look at all the smaller pieces that we can make propositions. So this big proposition now can be broken down into smaller propositions. Right? This roller coaster, over 18 years, over 5 feet tall. All this can be true or false. So the idea is that we want to be able to explain this, although this is written in English, a robot wouldn't understand it. So we must be able to explain to a robot this in some kind of a notation. So the notation would be, we'll say proposition P is, this person can ride this roller coaster. Proposition Q is person is over 18 years. Proposition R is over 5 feet tall. So what we need to do is to express this statement in a propositional way. So can you ride the roller coaster? So again, before we get to that formalization, if you're given this statement, obviously given a rider, given the age and height, you can write a program to determine whether the person can ride this roller coaster or not. But what we want to do is to think about this in a more formal manner. So for instance, this one, you have to think about what this means. For instance, if you say P unless Q, so if you have like ride this roller coaster unless Q, then that means if Q is true, then P is a false, or Q implies not P. So we'll look at some of those examples later. So operations and proposition. Two operations can be combined using operation disjunction, can be combined using the operation conjunction, and can be negated. So for instance, if you look at this one, these are the truth tables for the propositions. Propositions are either true or false. So you can see the proposition for the conjunction. That means for this to be true, both conditions have to be true. It says P and Q has to be true. If the proposition P or Q, only one of them has to be true. And the only time the proposition is false is that both are false. The negation is just negating it. So P and not P is, if it's true, it's false, and vice versa. P implies Q. So how can we think about this as a proposition? Let's construct the truth table. If you construct the truth table, you're going to find something like this. P implies Q. P implies Q means if P is true, the Q must be true. So for example, P and Q are both true, that means it's true. If P is true but Q is false, then the whole statement is false. Because you have to have the truthness here. If P is false, we really don't care. The Q can be true, therefore the whole statement is true. So P implies Q means that if you have P true, but it can be true, but it can also be false if Q is false. Now false implies false is true. That's kind of an interesting thing. So we'll talk about more examples like that. So the next step is to really look at some of these problems and see if we can figure out how to do these problems, and more details in follow-up videos.